So I'll quickly summarize what I did yesterday. So I just mentioned the two types of algorithms. One is the classical deductive type, and the one I'm going to talk about are basically the inductive ones, which is where you get samples sequentially and you try to learn something, infer something from that. So there are some, these are the kind of distinguishing characteristics. They're based on noisy samples and they make incremental changes. So you have some iterate xn which is changed slightly to make it to move to xn plus 1. And what you achieve is that computation or memory requirement for each iterate is low, though you are doing several such iterates. Each iterate typically is simple. And this is the archetypical algorithm, which is, it goes back to Robbins and Monroe, where mn plus 1 is a noise sequence which basically is uncorrelated with the past I explained yesterday. So it's like uncorrelated noise. An is a positive step size sequence. And this slide just shows that this additive uncorrelated noise is a general enough model, because anything of this form, the first display xn plus 1 is xn plus an plus, times f of xn comma xn plus 1. This is a typical learning algorithm where xn plus 1 are IID, and it can be reduced to the form of hxn plus mn plus 1 just by adding and subtracting one-step conditional expectation. These are the Robbins-Monroe conditions for step sizes, and people also do look at constant step size when they want to track some non-stationary environment. This is the Robbins. Okay, so what I'm going to do, or what I did yesterday, is to treat this as a discretization of a differential equation x not equal to hx, except that discretization, the time step I take n is a slowly decreasing time step, and there's a noise as well. It's a noisy discretization. And then the whole point is to show that if the differential equation converges, so will the algorithm. And more generally, algorithm tracks the asymptotic behavior of the differential equation. And if you again think of an as a time step, time increment, then the first condition, sum of an infinite equal to infinity, say that you are tracking the differential equation on the entire time axis, which is what you want because you are trying to capture the asymptotic behavior. And sum of an square being finite implies an going to 0, which means asymptotically the discretization error becomes negligible. But more importantly, this, under reasonable assumptions, this sum converges. So this is the noise being added. So if this sum converges, then the tail of that sum, which is the noise added from n onwards, goes to 0, and that implies in particular that the error due to noise also goes to 0. And this is actually, I'll skip this part, the intuition is here. What you do is you take the iterates plot, so define a time sequence tau n, tau 0 is 0, tau 1 is a0, tau 2 is a0 plus a1. So I treat a as time steps and define tau 0, tau 1, tau 2, etc. So that tau n is sum of I equal to 0 to n minus 1. And then I plot xn versus tau n and interpolate linearly. So I get this linearly interpolated iterates. Then on a moving window, I compare it with the differential equation trajectory initiated the same initial condition, and the claim is that they approach each other. And this is enough. This suffices to prove what I was claiming, that the iterates track the asymptotic behavior of the differential equation. I mean, for people who have a background in control or differential equations in general, proof is actually easy. It uses something called Grunwald inequality, which is quite standard. Okay, so if there's a Lyapunov function which tells you that the ODE will converge to some fixed unique equilibrium, then so will the algorithm. And more generally, you can say that it goes to some largest invariant set contained in the set of X where the gradient of the Lyapunov function vanishes. Okay, this is something I described yesterday. So this invariant set is called internally chain transitive in this sense that given 2 points, I can find a finite sequence of points in between, and given epsilon and t, the sequence of points in between, in between means somewhere in the invariant set, such that I can draw these epsilon balls around all these points, and I can find trajectories of duration bigger than t, which go from one to the next. So that you can start with the first and end up with the last. And actually, I mentioned Conley somewhere and said that I'll return to Conley again, but I didn't mention why. So see, I'll stick to this picture. I have some equilibria, some may be asymptotically stable, something like this. Look, I mean, this is a local statement. Some may be completely unstable, and there are some which have some stable directions and some unstable directions. And I argued that elsewhere it will look like this. Unless you are exactly on the stable manifold, you will move away. The thing is that if I throw in some other technical condition, namely if I see this, so this, suppose this is an unstable, okay, this is an unstable manifold and it intersects with this somewhere. I want to impose the condition that they are not tangential to each other, they sort of what's called transversal. So I'm not going to use that condition because I will consider only local behavior, but this kind of systems have a property called structural stability. You perturb them a little bit, the picture gets distorted or does not change. And since we are looking at these as limits of noisy systems, that if the picture is going to change with just small perturbation, if the ODE is such that small perturbation will completely change the qualitative behavior, the noisy algorithm is not going to, I mean, they cannot tell you much about the noisy algorithm. See, there are fairly exotic things that can happen. For example, something like this. There can be an unstable manifold which becomes stable manifold of this and so on. And it can, so this is something called heteroclinic cycle. So these are structurally unstable. So I'm ruling out these pathologies. Now, the reason I mentioned Conley is that, see, this picture, which, as I said, by and large, this suffices for at least optimization algorithms. But one can think of more generally, there's some kind of sort of limit set, what's called omega limit set for differential equation. I shall consider such limit sets which are which have an open neighborhood and are maximal with respect to this neighborhood, in the sense that any other invariant set is contained in it. So this is a maximal open set, there's an open neighborhood where in between there's nothing. What Conley did is to extend this kind of picture to general limit sets, just what he called isolated invariant sets, and more or less almost the same thing to go through. So if there are arrows are coming this way, it's not a point anymore. Then this is called an attractor. So there's a neighborhood in which everything goes there. If they're going away, it's called a repeller, and there can be in between situations. And every time I make a statement, I put in brackets attractor. So that's because a lot of this theory goes through for the Conley picture as well. Yeah, so the Benheim's this is a general theorem is that action will converge to an internally chained transitive invariant set. So as I said, as I mentioned last time, is the first point and the last point are identical. It's said to be chain recurrent, and what Conley did was to he showed that a dynamical system, ODE in particular, will have I mean the space splits into this chain recurrent sets and gradient, what he calls gradient like. So those will be basically transient part. Anyway, the whole idea is just that doesn't have to be a point sort of equilibria alone. It can be more general, and most of what I say will extend. So this is was to show that if it's unstable, then even if there's even if there's one unstable direction, almost all trajectories will move away, and because of the noise, you will be pushed off the stable manifold often enough. That's why I meant by noise being rich enough. It should be sufficiently strong in directions transversal to the stable manifold. If this is part of the stable manifold and the noise is also along this direction, nothing or not enough away from it, then it may not happen. So you have to put some conditions on the noise. So this is a law of large number can be exhibited as a stochastic approximation, just a simple manipulation. And then you get a linear differential equation which tells you that it converges to its mean. And same proof generalizes to urn models. This is a one-dimensional single urn, and you drop one ball at a time, one red or blue, and red ball, it's red with probability P of xn, where xn is a fraction of red ball at time n. So that leads to this picture. So this P is a function from 0, 1 to 0, 1, so it will have at least one fixed point, assuming continuity. So there will be at least one x star, so that P x star is x star, and then this equation being a scalar bounded equation, it has to converge, and it will converge to some x star. And more generally, so this is the sort of I wanted to highlight that this is kind of a equation for a probability vector evolving in time, in forward time. So I call it nonlinear Kolmogorov equation, because for Markov chains, continuous time Markov chains, the linear counterpart is called forward Kolmogorov equation. And that's the limiting differential equation for this iterate, where psi n satisfies the, so this should have been psi n plus 1. Conditional probability that psi n plus 1 is I given the past is pi of xn. Now this, of course, so in scalar case it converged, in general it need not, but you do find some, okay, so this is, as I mentioned, is studied extensively in what's called vertex reinforced random walk, where your probability of going to a particular vertex depends on how often you have been there. This is like positive reinforcement. I mean, it has been used to model things, behavior, or I mean, in economics sometimes what's called increasing returns. There's a person called economist called Brian Arthur who studied it extensively. So there are two roughly. He gives the example of that. I mean, now it's this video cassettes are gone, but in the days they existed. The VHS was the most common brand, and apparently when it came out, Sony had a superior product, but were very protective about it, and it did not spread enough. And because VHS spread and VCR players were designed for being compatible with VHS and so on, they completely captured the market, and Sony was pushed out. So this kind of phenomenon, not necessarily the superior technology wins. So this is so you use this kind of models for that, and of course they're modeled for herd behavior and so on. For example, standard example is there's two similar bars or whatever, or restaurants. No reason people should go to one or the other, but after some initial crowding of one, you see more people there, so you go there, so everyone goes to one place. So all these things kind of fit this nonlinear models. And here I just say that y dot equal to hy and z dot equal to at times hz have same trajectories if at is positive, and if the integral is infinite, they're same all the way to infinity. And then in the previous, the Kolmogorov equation, if I take at as this normalizing factor there and multiply it by that, then it becomes then that it becomes this equation actually. And this there are several, basically it's effect equivalent to the nonlinear Kolmogorov, but there are several equations which have this form, and this statement actually I got confused yesterday, it's correct. If I write Fi equal Fix is Xi Ui X, it becomes replicator dynamics. Because if I plug in Xi Ui X and then pull Xi out, it becomes Xi times Ui X minus sum over J of Xj Uj. And then I gave another equation which has been studied quite a bit. Okay, this replicator dynamics, there are a lot of talks already, but it's also limit for, I mean, you can see the similarity of the discrete iteration with nonlinear Kolmogorov. It's a multiplicative weight algorithm, which is extremely common in machine learning and theoretical computer science in general. So this is another example, which is Brown von Neumann Nash dynamics. I wanted to mention one more. I don't remember the exact form of FI, but long time back when I was in IISc, I had a very close friend called Sanjay Jain, who is now in Delhi University. He and his student Sandeep Krishna, who is one of the organizers. I don't know whether he's here. His thesis, they came up with some model for emergence of autocatalytic cycles, which are this kind of equation. Exactly the same, but different FI. Okay, so fictitious play, I will probably skip this because it's a lot been discussed. So this is the ODE limit of fictitious play. You are responding to the empirical policy of the other, I mean, it's a two-person game, and XI is the mixed strategy of I, and I mean, not necessarily two-person, sorry, n-person game, and XI is the mixed strategy of I at time t, which is updated according to the best response to what the others are doing. But X minus I at t is the empirical policy. I mean, so XI, you assign to each of the other agents a mixed strategy equal to the empirical distribution of his or her actions. That leads to some complications, as I mentioned. So this was one other. This is again congestion games, very specific to that. Where this UI xi raised to alpha is some kind of utility function which decreases with xi, which makes this what's called a monotone dynamics. The cross derivatives are non-negative positive in this case, and therefore for almost all not almost all, for generic initial condition, that means belonging to an open dense set, the differential equation will converge, and one can argue that the iteration will also converge. So this kind of says that I mean, it's used in traffic. So traffic will stabilize basically, and the alpha n to infinity limit, you get something called Wardrop equilibrium. So traffic will concentrate on only those routes, so that going to any other route is suboptimal. It's kind of a population version of Nash equilibrium. Very specific to transportation and I mean, networks basically. So it has been used extensively in communication networks also. So this is so this I mentioned because there's a lot of activity in the mean field games. So here the idea is that the transition probability of the Markov chain in addition to the previous state depends on the, I mean, there are multiple Markov chains, n Markov chains say, and the transition probability of ith depends on the previous state and an average over the states of the average of the transition probability over the second argument, which is the states of the other agents. So as n goes to infinity, you can write, so suppose I define pi n as this empirical distribution. So I didn't give any notation. So this is the empirical distribution across agents at time n. So if I let that go to infinity, then it satisfies the deterministic equation. So in the asymptotic limit, the coupling becomes deterministic. So the randomness remains due to its own random dynamics, which is independent, and the initial conditions. So if the initial conditions are independent, then the process become independent, remain independent through the time. So that's what's called propagation of chaos. And as I said, this is studied extensively. I sort of worked this out for discrete time. Actually, I think it has been looked at in discrete time, but most of the work is for diffusions. It's called Makin-Vlasov equation. This is a second class of algorithms or dynamics, which is useful. So this is gradient descent, which is a limit, I mean, the differential equation limit of stochastic gradient descent. And if in machine learning, you want to minimize some such, this is a mean square loss, but there are other loss functions also. And if you write the gradient descent for this, that becomes the, and for neural network, that's the backpropagation algorithm where the gradient computation is split over multiple layers. There are various clever tricks to simplify the gradient computation and so on, or speed it up. So this is just to show how adding a second order, making it like Newton's law, and add a second order term that makes smoothens it out. And so in landscape which are sort of narrow and slowly, suppose you are looking at a quadratic landscape which is like this, some bowl like this, which is very small this way and very large that way, then gradient descent will do very badly, but momentum method works much better. Sorry. It also escapes the shallow local minima because of the momentum. There is a subgradient. If it's not differentiable, then you can use this cone called subgradient and say similar ideas work. This is another class. So here the ODE is x naught equal to fx minus x. So, the nonlinear Kolmogorov was also of this variety, but here I am using some other property, namely that it's a contraction. Norm fx minus fy is less than or equal to alpha norm x minus y. And then one can show that norm xt minus x star is a Lyapunov function and it converges to the unique fixed point. When alpha is 1, it's a bit complicated, which I talked about a bit, but I won't get into that again. Stochastic ascent descent is basically to find saddle points if it's unistrict convexity and concavity in the two areas, the x and y respectively. And if x star y star is a saddle point, then the gradient descent in x and gradient ascent in y works, and that's because this is a Lyapunov function. So here I made a comment which I'll return to. For non-gradient schemes, one may have to separate the time scales. These are non-Lyapunov systems. I won't go into the details. The Smail's continuous Newton iteration. He showed that for almost all initial conditions, it converges to critical points. So in the optimization case, here it will mean hx equal to 0. Here it will mean grad of x equal to 0. But it's as an you have to be careful that for an optimization algorithm, it doesn't say too much. I mean, it doesn't say that it will go to a local minimum. But only thing it says is that it will go to a critical point. So if it is in a part where, if you are trying to minimize, and if it's in a part where it's sort of concave, it will go to a local maximum. If it's near a saddle point, it will go to a saddle point. Smail does not promise that it will minimize as desired. It just goes to some critical point.
Non-Lyapunov system means you don't have any fixed points, attracting fixed points.
No, if there's only a one minimum, the same proof will tell you that it will.
Then, so Lyapunov function is something which.
No, it's quite general actually.
Okay. No, where I'm confused is usually we read in standard text that Lyapunov function is something which you find by trial and error.
Yeah.
So how do I know a system does not have Lyapunov function? Is it?
No, that's it. All see, suppose there's a stable equilibrium point. Then in a local neighborhood, there's always a Lyapunov function. You can actually cook it up so that it blows up near the boundary.
So by non-Lyapunov, you mean globally a Lyapunov function does not exist?
Or rather, I'm not using any Lyapunov. See, this convergence is almost. It's not. See, Lyapunov will tell you something happens for all initial conditions. But here it doesn't. I mean, these are almost all points in two different senses. But generally, if you have multiple critical points, you can cook up a Lyapunov function which is high at repellers. In fact, that extends to the Conley theory. So there's a result in that theory which says that for all, there's a Lyapunov function which is 1 at all repellers, 0 at all attractors, and decrease everywhere else. So the existence of such functions, but it doesn't tell you how to find it. I'll skip this. So this is the cooperative dynamics. So basically, it says that your initial under that condition, if the initial condition dominate, the flows will dominate, and if the trajectories remain bounded, that's not free. I mean, you have to show that they're bounded. then it will converge for almost all initial conditions. So in discrete time, it has a lattice theoretic flavor. Actually, there's something called Tarski fixed point theorem. In complete lattices, if you have a monotone map, it has a fixed point, and there's a maximal fixed point and a minimal fixed point, and if you start above, you go to the maximal, start below, go to the minimal, and so on. In between, anything can happen. This is a continuous thing, so actually results are better than discrete. It has to converge. Nothing else can happen. So I had come this far, I think, roughly. So yeah, so this I described. This is just a distributed version. So some of these things I am highlighting, although this is kind of this kind of stuff is very technical and messy notationally. But if you are doing multi-agent things, it will pop up. It's unavoidable, unless you make it synchronous. You somehow ensure that everybody has exactly the same clock, etc. So here these are delays which, if you are using decreasing step size, they don't matter because the time scale squeezes them out, assuming they are bounded in some moment. The time scale is the decreasing step size will squeeze them out. I think I drew this towards the end. I was describing this. You have, so if I use an as 1 by n plus 1, the tau n goes like this, whereas actual time is this way. If I take some interval, it becomes smaller and smaller. The image becomes smaller and smaller as I move to the right. So if there's a fixed delay, capital T, it will shrink to 0 in the limit. So that's why they don't matter. I mean, the errors become higher, but asymptotics doesn't change. And this new IN is a local clock, which is convenient to use because you don't have to assume that everybody needs the same clock. And also it actually, you get better theoretical results with this. This is a problem. Not everybody is updating at the same time. And for that, under some conditions, like some step sizes, it's okay. Where if they're growing kind of logarithmically or slower, then the time scales, cumulative time scales match. So basically, sum of m up to nu in and sum up to n is asymptotically identical. So what happens is that if since each I is using something like nu in, the limiting ODE you get has that is x dot t equal to 1 by d times hxt, where d is the dimension of the ODE. The trajectory is just slow down d times. Otherwise, you get some nuisance like this, lambda t, which is a diagonal matrix with non-negative entries, which reflects the relative frequencies of updation. But this doesn't matter. For example, if they're bounded away from 0, it doesn't affect the convergence of gradient descent and the infinite norm contractions. So I was here. So there's two time scales. I have made two distinction between two parts of it. One is singular perturbation, and one is the next thing I call regular perturbation. Here, I split this into iteration into two parts and use two different step sizes, an and bn. And bn is by n going to 0. So the second iterate moves on a slower time scale than the first. So I call it so this kind of thing is called singularly perturbed differential equation, where epsilon is small, and you study it in the epsilon going to 0 limit. And the way you study it is that the fast time scale will treat. Let's go straight to this. So because yt is moving slowly, epsilon is small, I treat yt as a constant y, and suppose xt converges to some lambda of y, then y dot t will, instead of g of xt yt, it will essentially modulo some negligible error, track lambda yt, g of lambda yt yt. So suppose this goes to y star, then x and yn will go to lambda y star y star. So this is very useful in for algorithms because you can treat the fast time scale as a subroutine. So instead of within each update of the outer loop, you run a subroutine till convergence. You run both at the same time, but with different time steps, different step sizes. You will see examples in reinforcement learning of this. This I call regular perturbation, where I have some. There are variations of this, but I will just put some single object fixn plus this. So if this n was this second term was not there, it's just so suppose I define fn as n times iterate of the map f think I should have put probably superscript here because the subscript is ith component. Then basically you have the iteration xn plus 1 equal to f of xn. What happens here is that the limiting ODE is something like this, where I mean, forget basically you get something which the ODE gets modified by what's called the Fisher derivative of this map F. So this has been used for, suppose you want to do a projected. There's also projected versions of stochastic approximation algorithm. Suppose you want to do a projection operator, want to implement it in a distributed fashion, you can. That's one place this is used, but there's more important thing I want to point out. Okay, so this is what's called a regularly perturbed ODE. The difference is that in the previous ODE, if I put epsilon equal to 0, the dimension changes. So that's why it's a singular perturbation. Here it doesn't. Okay, so if I put epsilon equal to 0, still the d-dimensional.
But what if F2 has higher power of x in it? Let's say F1 has x square, but F2 has x cube.
No, that you will have to analyze case by case. Generally, generally one assumes that F1 all functions on the right hand side are Lipschitz, for the simple reason that the theory is clean for that. Anything else you will have to do case by case. So typically, if it's not Lipschitz, so for example, if you consider xt equal to 1 by 1 minus t, starting at 1, at t equal to 1, it blows up. So if you differentiate it, you get I think you get x dot equal to x square. So it's not non-Lipschitz, so this solution can blow up in no time, in finite time. So that kind of thing you want to avoid. But on the other hand, x dot equal to minus x cube will be stable. So if it's non-Lipschitz, some higher growth, you try to look for a Lyapunov function. See, if you have a Lyapunov function whose gradient grad v dot the drift is less than 0 outside a bounded set, not everywhere, that's enough to prove boundedness of trajectories, because it will be pushed, trajectory will be pushed to that set. Once it's inside the set, what happens is a separate thing. But you can also use Lyapunov functions just for proving that the solution doesn't blow up. So you have to use some such trick for in general.
So where I got confused is usually in singular perturbation theory, you say that no new roots are sort of not there when you put epsilon equal to 0, right?
Yeah.
But here, suppose F2 has x cube kind of term, and F1 has x square kind of term. If I put epsilon equal to 0, suddenly x cube roots are gone. So then would I call it singular perturbation or still regular perturbation?
I don't know. Generally, I have been, so far in at least in the learning scenarios, I have been working with fairly tame F1, F2. So just one paper by, I forget, multiple authors, but I'm not sure if they look at this issue. I think the main result is that you can kind of look at this as x dot equal to ft restricted to the invariant manifolds of x dot equal to f1. So this is the thing which I wanted to emphasize. This is pure average. So here actually this again is something I want to emphasize because it will pop up in distributed multi-agent kind of thing. I mean, it's extensively studied actually. So here I made it a superscript because it's each xi is a vector. So xi sub j is the jth component. I stands for a processor or a agent, and what the ith agent is doing his own stochastic approximation. But instead of taking just its own previous type xi, and it does an averaging over neighbors. Right? So think of the agents of processor sitting on a graph. So each processor at time n takes some average over iterates of neighbors, including himself or herself, and then so you can think of this as a actually this situation by itself has been studied as well, and it's called a gossip algorithm for consensus about opinion, consensus of opinion in such models like the deGroot model and variants. So this, many variations of this have been studied. So I'll call this a gossip component and this is the learning component. So what you are trying to learn or evaluate is this part, which is on a slower time scale. So the limit behaves like this thing. So basically here, so again, like that, what these people say, show, the simplest case would be this will be confined to the invariant surface of P, which is the vector of constants. So that shows that actually I have that all of them will track the same equation. So if it's a distributed gradient scheme, I mean, people are trying to minimize the same function, say, not non-convex function, but everyone has his own different observations, noisy observation. They will converge to a common local minimum. So this was originally studied by, it's a work by Tsitsiklis, Bersekos, and Athons, who were part of John Tsitsiklis' PhD thesis. And then a lot of people have sort of gone well beyond. In particular, if I make this P depend on, replace P by P sub xn, then I will get a slightly more complicated thing. And then this pi will get replaced by pi sub zt. You can exploit that fact to improve on the algorithms a bit. Okay, this is see this. All the analysis assumes that the iterations don't blow up, and that's not free. I mean, it has to be verified. And this is one test. Anyway, there are more than one test, but this is one convenient one. And so you just take this limiting. Actually, this again is used for reinforcement learning where it's linear growth. So what it does is to pick up this h infinity x assumed to exist, will pick up the linear term, and if the corresponding thing is asymptotically stable to origin, globally asymptotically stable, then the algorithm doesn't go up. So what your intuition is that when you have some dynamics, you look at the dominant growth term, which is so hx is say sum of some terms, which is the fastest growing term, and if that is kind of pushing everything down towards zero, that's enough to prove stability of the iterates. And this is something you sort of this is also a messy affair. Sometimes you get do not get an ODE limit for iterations. For example, if H is discontinuous, you are stuck with this. So for example, this is so for fictitiously in general. And you have to assume that this is not too much to demand generally. It's a non-empty closed convex. Actually, I should have said compact convex set-valued map, so that this graph is closed. Yes, I should have said non-empty closed bounded convex set-valued map. Then that will ensure existence of a solution, but of course it can have multiple solutions. And sometimes if in the discontinuous right-hand side case, this Gx is taken to be this. So take some epsilon neighborhood, its image, its closed convex hull. And intersection, if I took only this much, is called a Krasowski solution, but usually also takes, oh, I think I forgot to, I should have removed a null set out of here and then take an intersection. You throw out zero major sets also, and that sometimes gives a tighter Gx. That's called a Filipov solution. Anyway. It doesn't matter because I am in finite dimensional spaces, so they're all equivalent. Yeah. All usual norms are equivalent and compatible. LP norms, basically. If you change the topology itself, then it will be something else. Okay, so now I'll come. So last time there was a question on the Langevin limits. So the thing is, if you look at this as a, so far my algorithm was just this term. So think of this Mn plus 1 as a, yeah. Yeah. So what kind of stability is that? It's just a boundedness condition. Yeah, almost sure boundedness. Yeah. So it's nothing like Lyapunov stability. It's not like you can arbitrarily start close enough so that you stay as close as you want. No, this is a stochastic process, so you cannot guarantee such things. Because the noise can be persistent. See, stochastic Lyapunov for Markov chains, etc., the Lyapunov conditions only tell you that they are recurrent or positive recurrent. I mean, of course, there are some people do study some cases where they convert somewhere, but that's not common. Yes, so think of this as a kind of intrinsic noise or some measurement noise or something. And suppose you are also getting some extra noise from outside, then the usual logic that it should be uncorrelated, etc. So it should be like adding independent vectors. So you expect some kind of a square root behavior. I'm just sort of trying to motivate this. Not sure if it's perfectly convincing, but anyway, suppose you have some noise or you add some. You might even add yourself because the results are better. So if I add the square root n noise, the sign or IID, this is not important, but suppose they're Gaussian, then you get a stochastic differential equation limit. So this is called a diffusion process, and the Markov process with continuous paths is called a diffusion. And suppose it has a density p x comma t at time t and a stationary density p star x, in the sense that t tends to infinity, p x comma t goes to some p star x.
So even in the absence of your m, the intrinsic noise,
yeah,
you do get this equation only, no?
Yeah. In fact, for this, the intrinsic noise is basically get killed by n. Because that n decreases too fast for the noise to be seen in the limit. Square root n will decrease slower. So for example, for algorithms, you may often add some small square root n noise. So suppose script L is the differential operator, and that's gradient minus grad v dot grad f and half trace of sigma sigma transpose H f. Then pxt satisfies this forward Kolmogorov equation. Script L star is the formal adjoint, whatever you get from script L by, if you integrate, write script L g times LF dx and integrate by parts to get minus integral L star g times f dx. L star, that's the L star. I might have it explicitly somewhere. So the adjoint operator. And I assume that the initial start at a point mass. So because I probably didn't mention anywhere, I have to assume that sigma sigma transpose is non-degenerate in the sense that I'll assume all nice conditions. So the smallest eigenvalue of sigma sigma transpose should be bounded away from 0. And let's assume there are multiple typos. It should have been H. No, sorry, I am looking at the gradient system, right? I'm not. Okay, from this point onwards, H is minus grad V. Because I think initially I'm going to talk only about the gradient system. So H is minus grad V, and define this operator, and then the forward equation is this: del by del t. P is the adjoint of this operator to P. And as t tends to infinity, you can expect this to go to 0. I mean, of course, not free, but assuming that the diffusion is positive recurrent, then it will happen and you will get some density in the limit. So all this requires, the existence of density requires that condition. It's a sufficient condition that's a non-degenerate, and I'll also assume that it's at least continuous or Lipschitz. if it's only measurable, you lose uniqueness of these things. And if it's time dependent, so okay, yeah, I do have it function only of x. So if I have xt comma t, then even if it's continuous, it may, you may have problems with solutions. If it's only measurable in t, you can have problems. Anyway, these are all technicalities, but just assume that everything convenient holds true. So this like Markov chains, you have this Lyapunov function of namely the relative with the Kullback-Leibler divergence with respect to the stationary distribution serves for the forward. So this forward equation is the equation for the density in forward direction. And this will tell you that it will converge to P star with this as a Lyapunov function. And actually, it's not recent. This work appeared in, I think 86, I don't remember, or 90s, I don't remember, quite a while back, more than 20 years back, by Jordan, Otto, and Kinderlehrer, which showed that if you consider this metric, this is called the Wasserstein's 2 metric. So this is the metric between two probability distributions, which is infimum of this L2 norm over all x's with all pairs x comma y, where distribution of x is mu, distribution of y is mu. You don't the joint distribution is left free. So all pair distributions such that the marginals are fixed at mu and nu. So this defines a metric. I mean, if you take p norm, you get Wasserstein p. And what does Jordan, Otto, and Kinderlehrer did was to show that this actually works. The forward equation is like a gradient descent of this. This thing decreases. I mean, what do is they discretize, and from each step to next step, they sort of get the next distribution by minimizing the conditional Wasserstein metric. And what they show is that it's actually you recover a discrete version of the forward equation, and as the discretization is made arbitrarily small, basically, I mean, in that sense, it behaves like a gradient descent of with respect to the Wasserstein metric. And the reason it has become popular is that this, although information theoretically the right thing to do to compare probability measures, it's not very useful because it's often infinite. So suppose I am taking empirical distributions, I am doing some density estimation and just taking empirical distributions as the estimate. The empirical distribution at any time sits on, I mean, the histogram or whatever, sits on a finite support, whereas the limiting measure may be density may be continuous, so this will always be infinite. So it's not, it's too rigid, although mathematically very nice. So, is it continuous, that function, here divergence in Q, like is it weakly continuous? It can blow up, no. That is a problem. There is a problem. Yeah, because see, if P star is a density and Q is a density which converges to something singular with respect to P star, it will blow up. Then how do you use the Lyapunov function? No, because for a diffusion, they're all they have strictly positive densities all the time for a good diffusion. They're always absolutely continuous with respect to each other. So only on absolutely continuous measures it will work. The continuity. Yeah, generally one replaces this. I will come to that later. You replace this by the Rado-Nikodym derivative, likelihood ratio. Yeah, so people decided instead of looking for this kind of discrepancy measure, use this because it's much more generous. And so particularly for studying robust optimization or robust machine learning, they want to say optimize something with respect to model errors which are within a Wasserstein ball. So then again this Jordan, Otto, Kinderlehrer article was rediscovered, and now there's enormous amount of work on that. Yes, actually, I already sort of use this. This is called Langevin. So okay, there's one difference. I replace sigma xt by square root 2. This is called a Langevin algorithm, and the T is called the temperature by analogy with statistical mechanics. Stationary distribution is this, and Z is the normalizing factor. And it concentrates more and more on the global minima. That's easy to see more or less. As the T goes to 0, I think there's some minus missing. As T goes to, there should be a minus V. So as T goes to 0, this will concentrate more and more on the global minima of V as T. And that's the basis of the optimization based on Markov and Monte Carlo. You run this diffusion for a long time and then take the mode, the most frequently occurring value, and that's good estimate for the global minimum. There are, of course, improvements on this also. So you discretize it and use some kind of each time the random variable distribution you get, use that as a proposal distribution for a discrete MCMC. That's called Mala. That's the current, I think, probably the current front runner. Metropolis adjusted Langevin algorithm. There was a question last time about what happens to if they have multiple global minima. So suppose there are multiple global minima. Sorry. Intentionally drawing like this. So that has been analyzed for the gradient systems. So what happens is, I will just give an intuition. The proof is the whole paper by somebody. So see, these are points global minima where grad V vanishes. Suppose I take this as x star. Grad V x star is 0. So if I write the Taylor expansion for Vx, so suppose the minimum is 0, let's say. Anyway, it's something deterministic. Then the significant term is the second order term. So it will be Hessian Vx star and x minus x star. It's in the neighborhood. It's a strictly local argument. This suggests that it should be Gaussian-like here in some sense. And sure enough, the weight they get is determined by the determinant of the Hessian. There's a paper by Chirue Wang. If anybody is interested, I will have to fish it out. I don't know, remember. I forget Wang, I think. I don't know whether it has been done for more general dynamics, but certainly it should be possible for more general dynamics as well. But this is true. For gradient systems, certainly it has been done. So typically the narrow one, the bigger the basin, the better you are, there will be more mass. Yeah, and essentially then you can let this TT go to 0 in probability to the, sorry, you let the temperature decrease slowly, then you get convergence in probability to the set of global minima. This I have highlighted because it's not with probability 1, it's a weaker notion. And the optimal cooling, this is called cooling schedule, is C by log T, where C is this object where lambda T is the spectral gap of L as a function of T. And okay, so maybe I'll first explain this way. Convergence, I mean, probably many of you know this already. So convergence of xn to x in probability and xn to x with probability 1 are different. This is called also almost sure. These are much stronger conditions. So this is that the probability measure of the set. So if you consider this set, the sample point omega such that greater than epsilon, probability of this goes to 0. But this set can wander all over the probability space. So you cannot say anything about omega. It may not converge at each omega, every omega in fact. You can cook up examples so that the random variable does not converge at every omega, but it converges in probability. Whereas this, by definition, outside of zero probability set, it will converge for all omega. So you have a weaker convergence notion, and whether it converges does any better than probability depends on the. So this is the global minimum, depends on the how deep this thing is. If it's sort of like this, very shallow, then it will wander once in a while. But the wanderings will become rarer and rarer. Yeah, so if I write P star, that particular distribution, dq by P star is given by this, and so if I forget the constant term, you get this object. So this is again, I'm trying to make connections with physics. So this like the Helmholtz free energy, this is entropy, and this is some average Hamiltonian. So this is what is so. Actually, sometimes I have seen sort of convergence of in probability books, convergence of Markov process to stationary distribution, and this fact being compared with entropy maximization. But it's actually the correct statement is this: it's not an isolated system. It's more like a system in contact with an infinite heat bath because of the randomness. Except that if you this is average energy, so it will go to the stationary distribution, which minimizes average energy minus. I'm missing the T here. There should have been a T. T times the entropy. Equivalent, you can pose it as a constraint optimization, maximization of entropy subject to some energy constraints, or the other way, and then you get the temperature appearing as a Lagrange multiplier. And this, at least in probability theory, is called the Gibbs variational principle. The fact that minimizing this leads to what is called the Gibbs distribution. I don't know. Is the same terminology in physics? Okay. So it's what's called the Legendre transform of the concave function. Free energy is a Legendre transform, and I just want to mention this one interesting fact. I don't know. It makes contact with optimization. That's why I like it. So these are concave functions, but in convex case, suppose you have one convex and one concave, the minimum vertical distance between this equals the minimum vertical distance between pairs of parallel hyperplanes separating them. So this is the pictorial statement of what's called Fenchel duality theorem. So it's a dual optimization problem, and if your energy function has some kind of a flat patch. Okay, so when you take Legendre transform, you end up basically you take a say plane with some fixed given slope, and you move it till it just touches this. Now, if it touches at a point, no problem. But if there's a flat patch, then in the dual there will be a kink. It will become non-differentiable here. There's a one-to-one correspondence between these, and this corresponds to multiple phases here, and it shows up as a non-differentiability in the dual. Is this well known? And the final fact may be well known, but the convex optimization picture. No, but this fact.
Flat patch is probably not done.
This is in this very nice article I strongly recommend by Alan Whiteman. Not an article, actually, it's the introduction to a book by Robert Israel called Convexity in the Theory of Lattice Gases. It's 1/3 of the book is the introduction. It's extremely worth reading. I think I already said this. Okay, so in general, you have this thing, considers again something with multiple isolated equilibria. And okay, I should have said stable equilibria or attractors. Then at t goes to 0. So here I have come back to hxt, it need not be gradient system, but you have similar results available where the small noise limit as t tends to 0 will, the stationary distribution concentrates on attractors that minimize something called Friedlein-Wenzel quasi-potential. So this is, it actually has this form. So this is actually a kind of a, I mean, those who know, are familiar with control, it's a dynamic programming equation for a certain control problem. Basically, if you have, you have to kind of push something against the flow. So I minimize this object. It's kind of self-referential, except that this Q are taken only at the equilibria. Consider I reverse the flow and add control to it. So I have to kind of push it away from the original attractors towards something else. Push it against the original flow towards some attractor, and the minimum energy. So you may do that only asymptotically. So this is the energy taken to push this trajectory to AI minimum over all I. That gives you the, and this gives a selection principle for equilibrium behavior. And this is attributed to Kolmogorov. Apparently, he never wrote it anywhere, but this is an article by Ekman and Ruel on ergodic theory of chaos and strange attractors, where they mention this, that for an ill-posed problem with so ill-posed means no solution or non-unique solutions, or solutions not depending continuously on the problem data, but this is for specifically for non-unique solutions case, just add noise. And as in the case of non-Lipschitz ODE, suppose you have h dot equal to h, where h is continuous but not Lipschitz. There can be infinitely many solutions at every point. But if you add noise, the stochastic differential equation is well posed. So you add noise, things become better. And then let noise go to 0. And if you are lucky, there will be only one unit. If not, hopefully not too many. And those are the physical solutions, because as Kolmogorov believed, there is always some noise. So nothing is exact. So our models are certainly not exact. So no, this is a definition of Q. I am cooking up a. So there is no constraint on you? Yeah, you can be anything. I mean, it won't, because there's a quadratic penalty on control, it won't blow up. See, this is kind of, you can add some constant to Q, it will still satisfy this equation. So it doesn't have unique solution. So at best, modulo constant, additive constant. But this is what I mean, Kolmogorov proposed, that there's one specific instance, add noise and let noise go to 0. And actually, this is what this paper of Foster and Young does for actually this. I think there's probably replicator dynamics plus noise, if I remember. And the limit they get, they call it stochastically stable Nash equilibria. And again, as I pointed out here, it's actually the how broad is the basin seems to play a bigger role. So for small positivity, it's the okay. So the Friedlein-Wenzel go further. So if there are multiple attractors, the process is like a Markov chain. It will be near one attractor for a long time, then jump to another, and then jump to another, etc. And it it can thought of as a Markov chain on attractors with the probability proportional to this. And this action functional is what you expect. It's this. Of course, I just taken square root t. That's why it's it's just this. Otherwise, there will be sigma sigma transpose inverse somewhere. And this is defined for any differentiable trajectory from one equilibrium to another. And as you expect, as the noise goes to zero, basically you will get the optimal trajectory. This is part of the Friedlein-Mendel theory, and this actually is. I mean, here I am considering trajectory between two equilibria, but if you just consider finite time diffusion, it's the same action functional. This is a whole theory, the entire book by Friedlein and Mendel called Random Perturbations of Dynamical Systems, which does a lot, this and much more. Now, this also sometimes is this also gives interpretation through something which is routinely done. So if f is a bad function to minimize, you can it can have arbitrarily complex. For example, you are fitting a polynomial. The more degrees you allow, the better it will fit. There's some quotation that if you give me 5 points, I'll fit an elephant or whatever. So you want to penalize. There's some complexity penalty. You don't want to allow very complicated models. So, for example, this is a common penalty in, for example, in image processing. This kind of thing is used. So you can think of this as a sort of putting some prior that penalizes the complex models, and then again this will become again. This is like negative entropy, and sorry, I shouldn't say that. This is one specific instance of it. Yeah, this I already said. Okay, this is the part I said that there's some part which is more abstract. This is one. So I'll just try to give a verbal description of it, because it is there is non-trivial work in learning on this aspect, particularly in some economics literature. I have found some. So this is just Bayes' rule recalled. The probability. So y is observations, x is the parameter. So probability that x equal to I given y equal to j. You want to estimate the parameter given observations. This is the Bayes' rule. It allows you to. So I'm assuming that you know these objects, and you want to basically, given py equal to j, given x equal to I, and x equal to I, you want to invert and get the conditional probability the other way. So advantage is that many Bayesian computations are recursive. It's particularly true for state estimation. For example, the Kalman filter is computable because it's recursive. It's Bayesian object. The drawback is that in many cases, except in the linear cases, etc., you have to compute this denominator, which is very computationally intensive and needs separate algorithms like MCMC to manage. And often this is true for the economics literature, which I am going to mention later. So the strong assumptions such as absolute continuity of probability measures on infinite product spaces is extremely restrictive. And because of that restrictive nature, it leads to some nice results. So see, I said that this is more advanced because it uses major theory. So in particular, this what's called Radon-Nikodym derivatives. So let P not be two probability measures, and I did show by E and E naught the corresponding expectations. So say that P is absolutely continuous with respect to P naught. And this is the notation. If P naught A is 0, means implies P is 0. That means what's impossible under P naught must be impossible under P. Okay. Said to be singular with respect to P naught if they, and this is denoted by this perpendicular, if there's some set A such that P naught of A is 0 and P of A is 1. So they sit on two disjoint sets. Okay. So in general, neither may be true. So your P equal to alpha P, this is always true. This is called Lebesgue decomposition. P is alpha P naught plus 1 minus alpha P1, where P is absolutely continuous with respect to P naught and perpendicular or singular with respect to P1. So this is convex combination of I should write alpha. Thanks. Yeah, between 0 and 1. Yeah. There's a further decomposition of P1 also, but I won't use it. P1 can be partly atomic, that means Dirac measures on points, and can be partly sit on something like Cantor set, for example. Something, a zero measure set which is not a point. But we won't need that. So if P is absolutely continuous to P naught, then there exists a random variable lambda non-negative such that E naught lambda is 1 and any expected value of any y with respect to E is E naught times lambda y. And the lambda is called a Radon-Nikodym derivative. And if the P and P naught are measures on Euclidean space with densities P naught, lambda is just the likelihood ratio. So think of lambda as likelihood ratio. So suppose I take this infinite product space and this is a typical element. So the space of sequences in R and X sub n is the n string in the beginning, x1 to xn. Rn will denote just x1, the R cross R cross, the first n spaces, product of first n spaces. And suppose this positive densities exist. So instead of working with the Radon-Nikodym derivative, the general theory works for Radon-Nikodym derivatives, but I'll stick to densities. So I have these densities, I can write them as some initial ratio of the likelihood ratio of the initial condition and the conditional likelihood ratios. Suppose this is all true. Then lambda n will converge to some lambda infinity with probability 1. This actually is true in general. One can show that lambda n, the Radon-Nikodym derivative of the probability measures P and P naught restricted to the first n product space. They form what's called a martingale, non-negative martingale, and this convergence is always true. It's actually a trivial case of something much more general called martingale convergence theorem. But so this expected value of lambda n is always 1 because Radon-Nikodym derivatives. That's easy to see. If I put y equal to 1, then I'll get E naught of lambda equal to 1. So, but in the limit, it can lose some mass, so it can be less than equal to 1. It remains non-negative, but less than equal to 1. But if it is 1, this is a fairly restricted, what I meant by restrictive condition. Then the limit, if Pn, let Pn and P naught n be the restrictions for P naught to the first n. If Pn is absolutely continuous with respect to P naught n for each n, that does not imply that P is absolutely continuous with respect to P naught. But if the limit has expected value 1, then it is true, and the limit is the Radon-Nikodym derivative. Now, on the set where lambda infinity is positive, I can define lambda n plus 1 given n as this ratio. That tends to 1 because both numerator and denominator are converging to the same object. So, but this turns out to be the Radon-Nikodym derivative of this conditional probability with respect to this. And therefore, the ratio tends to 1. So in this sense, the future conditioned on the past starts looking the same as n goes to infinity. So, but the problem is that this is only on this set. So if lambda infinity has expected value 1, so if P is absolutely continuous with respect to P naught, then this is true almost with probability 1. And then that's when you can make non-trivial statement. For example, expected value of something with respect to conditional expectation of any random variable y given history till n asymptotically under P and P naught asymptotically agrees. I have said that here. Okay, so this is called asymptotic agreement, but it's useful when it's true everywhere. So y given past till n. This goes to 0. So this is an ancient result due to, I think, Blackwell and Friedemann most probably. Blackwell is certainly there. I forget second author. It was called merging of opinions with increasing information. They have stronger results than this actually. But anyway, so it goes a long way back. But it has been used to some paper by Kalai and Lehrer, which uses this kind of ideas to show that in repeated games, agents converge to the sort of agree on some common, asymptotically converge to an equilibrium. Even if they start with different P and P naught, but the P being absolutely consistent with P naught is a restrictive condition. Sorry. So, see, you get kind of two drastic scenarios. We will go to the next one. So what happens is that on the part on the set where lambda infinity is positive, the conditional distribution will agree asymptotically. Elsewhere, they will fully disagree. I mean, something will be possible for one and impossible for the other. That's a related body of work where in engineering, where people exchange infinitely many estimates to each other. There are multiple agents trying to estimate something, and there actually this has been proved more precisely that they start with a common prior, but the models may be different. Sorry, if they start with a common prior, that means the models are, and the model, I think I didn't write the complete statement. Yeah, I think this kind of incomplete. So this is a similar scenario, except that people are also exchanging estimates. So what happens is that where on the good set they completely agree, on the other set they completely disagree. So this has certainly been proved in this scenario. I am not sure whether anybody has looked at it in the game theoretic framework. So we'll probably finish this part. This is also, I mean, I'm again including it, is similar. I'm including it for sake of completeness because it is sort of, people do look at it. As you can see that compared to stochastic approximation, I mean, it's not algorithmic. That's why I'm slightly unfriendly to this kind of work. Yeah, so again, same scenario. I have Pn and P naught with these restrictions, and lambda is the likelihood ratio. Then again, same thing. And suppose I consider IID values with distinct laws or time homogeneous Markov chains with different transition functions, then if P naught is the true probability measure, say, then lambda n will, okay, so I consider likelihood ratio of P1 with respect to P naught and P naught with respect to P naught. Let's just take 2, or let's say, I've taken only 2. Then on this, if they are singular, then the radon negative derivative will go to 0. Because if it was positive, non-zero with positive probability, their conditional laws would have their laws would have asymptotically agreed, and that I have assumed that they remain distinct, so they are not allowed to agree. So, for example, if you take IID random variables with even slight difference, suppose a Gaussian with mean 1 and with mean 1.0001, you may not care, you may not think they are different, but in the infinite product space, they are singular because the laws do not agree. So it's a very rigid requirement that on the infinite product space they should be absolutely continuous. That's one of the objections I have about the previous Bayesian learning. But here it advantage, because if suppose you have a finite family P theta, of which this one, maybe I have that here. Okay, so suppose we have a family P sub theta where theta belongs to a finite set and there's a true parameter theta naught. And I consider d P theta n by d P theta naught n. Okay, so likelihood ratio over n. then and assume that the p thetas are distinct for different thetas, then the likelihood ratios will go to 0 for theta not equal to theta naught, and it will always be 1 for theta equal to theta naught. So you take the maximum likelihood estimate, it will converge to the correct parameter. You can also take the log likelihood, and then it becomes the analysis becomes easier because you use the law of large numbers for IID or Markov chains, and you get this. Basically, if you take apply law of large numbers to log likelihood. So I have written, I am taking it, writing this for Markov chains, this lambda n plus 1 given n. You get the Kullback-Leibler divergence again. So there is 0 if the measures agree, or otherwise strictly positive. So this, I already said this. If I take theta hat n to be the arg min of lambda n, the should have been arg max here, then it will converge to the true parameter. So this is a non-Bayesian estimate because I didn't have to put any prior anywhere. And in the asymptotic stationary case, if the true parameter is not there, it will go to the best estimate with respect to the Kullback-Leibler. And so this is okay for finite collection, but if this is not finite, then you need the convergence, this convergence to the Kullback-Leibler to be uniform in theta. Otherwise, because you want convergence of maximizers, not for each theta, but the maximum of theta. So I think I've probably finished in good time. Yeah. So let's start something else next time. Any questions?